Right, connected particles. So we are dealing, when we're dealing with connected particles, we are nearly always dealing with things which are moving. And as we found yesterday, that gives us the combination of F equals ma with suvet. And in addition, when you've got two connected particles, you may remember when we did this last year, which was either things towing each other along horizontal surfaces or pulleys. And lifts, things in lifts. We either dealt with the different parts of the problem separately, or as a single thing, so together. And so I suspect today we'll come across all four of those things in different combinations. So let's have a look at a couple of example questions. We've got here what I reckon is a fairly classic connected particle question. We've got one particle on a rough slope, so there is friction, and that friction is marked for us in the diagram, may not be, but it is opposing the movement. And we've got another particle dangling, and common sense tells us that unless friction is really strong, the 10 kilogram particle is going to cause B to fall. But they confirm that by telling us in the question that B is released from rest and falls to the ground in 2 seconds. So Joe, tell me what both A and B will have in common, or what will be the same in this problem when we let B go.
Acceleration.
So the acceleration will be the same. So we are almost certainly in this one going to deal with A and B separately, to start with at least. But we know that between them they're going to have the same acceleration. Jacob, what else will be the same in this diagram?
The velocity?
Well, the velocity acceleration will be the same, yeah. It's the tensions. So those two tensions will be the same, and that's specifically because the thing connecting them is being modelled as a light, inextensible string. Light, it has no mass, inextensible, no energy is being lost in stretching it. So between these two, we know that T will be the same in both, and A will be the same in both.
Well, can you do big T? Looks like time.
There we go. So Aidan, where do you suggest we start, and which do you think it's going to involve, if it was MA or SUVA? And there's no real correct answer to this, we'll end up doing both, but where would you start with this problem?
I don't know.
What do you reckon, Stasha?
SUVA, I don't know.
Yeah, you're going to SUVA. Which bit are we going to SUVA, A or B?
B.
B, yeah. Because we're told about B, aren't we? We're told that B is released from rest and falls vertically to the ground in 2 seconds. Are we told D? No, we've got to find D. Okay.
There's a big camera in the way from them.
Sorry?
Is it possible to move on?
Sorry, for those watching at home, we're just moving the camera for the benefit of Joe. Sorry for feeling a bit queasy. This would all be edited out if I knew what I was doing, but there we go. Yes, sorry. Yeah, so let's zoom out this side. So fill in what you know. We're trying to find D, which is the distance. equations on the formula sheet.
So I'll get working on
Now I suggest that we don't worry about V because we don't know, but we know that A is going to be in common. So I'm just going to fill that in as A. So I'm going to say, right, I'm going to use S equals UT plus a half AT squared. U is 0, so that's always great news, isn't it? So D, which is the distance we're after, is equal to a half of A times 4. So that's 2A.
Still drawing that.
It's on page 100 and, well, you can read, 132. Emma? Just talking about connected particles. Oh, no, the camera's doing that one. It's okay. It's all good. It's all good. So we haven't got a value for D, haven't got a value for A, so we now need to move across to this, the A particle. And so John, what approach are we going to use on the A side? Is it going to be SUVA? Is it going to be F equals MA? F equals MA, that's right. So go on, see if you can get somewhere with that. So it's moving that way, so I'm going to call that positive.
Where have you got the equals for A from?
F equals MA, so A is the acceleration, for M is for the mass is 4 kilograms.
Yeah.
Remember, vertically it's in equilibrium, so we've got forces up, equal forces down, no acceleration there at all. And don't forget the other rule, which I perhaps should have written down here. Oops.
So take the coefficient.
Yes, 0.7.
What did you do from there?
So I've got f by resolving vertically, which is odd, isn't it? That I work out a horizontal force by resolving vertically, but it's because of this relationship between f and r. So I can then sub that into here, but I've still got two missing values. I don't know t and I don't know a. I know that d is equal to 2a, but that still doesn't help me. So what's the thing we haven't done yet? What's the final piece to the puzzle?
B.
What haven't we done with b?
Got an expression for t involving s.
So we haven't done the resolving bit. We haven't done f equals ma for b, have we? We've used suvat for b, and that's got us to d is 2a. But the last piece of the puzzle is resolving, and there's no point in resolving horizontally for b, but it's a really simple resolve because we've only got, remember, we're just thinking about, we can't see this, we're just looking at b on its own. So b is just a force going down, a force going up, and an acceleration going down. It's accelerating downwards, so I'm going to call downwards positive. So I'll write my d equals 2a at the top here, which is what I got from the suvat. And now I'm going to resolve vertically, but I'm going to consider down to be positive. So f equals ma. Now I could solve this as simultaneous equations because I've got two equations with t and a in. So I could line them up like GCSE simultaneous equation questions and just whack them into my calculator. The problem with doing that is that I've got rounded values and there's no easy way of getting values I've stored in my memory into the equation solver. So I like to use substitution. It's not the only way of doing it, but I like to use substitution. So this tells me that t is equal to 9g, which is 9.8, take away 10a, which I don't know a yet. So I can then substitute that into this equation. And when I substitute it into that equation, I've now only got a. So I've replaced f with 23 point whatever. That's stored in my calculator memory. I've replaced t with 10g minus 10a, which I got from my b resolution. So that's just going to give me an equation involving a. Run out of space, so I'm going to do all that up here. And I've deliberately not reached for my calculator until now. I've stored the value of f on my calculator, but I think that's the only one I need to store. So I've got 10 times 9.8, I can do that in my head, 98. Take away the value I've stored, take away 15 cos 25, divide that by 14, gives me a value for a.
9 I got.
Sorry, yes, 3A. But I'm not, I don't want A, I want D.
Ooh.
Qu'est-ce que c'est?
Well, it's not looking good for me, to be honest.
It's not looking good.
You could both be wrong.
Well, I know I'm right because I've got the answer in front of me. So D is 8.77 meters. There's a lot going on there. A lot going on.
How many marks would that be?
I don't know, big question, and that's just part A. But although there's a lot going on, we only did stuff that we've already done. So we did SUVAT for B, and that was nice and straightforward. We did resolving horizontally and vertically for A. Resolving vertically didn't seem to make sense because it's not moving vertically, but that's necessary to work out F because of the relationship between F and R. And then we resolved vertically for B. So none of that was particularly new. It did give us some fiddly algebra at the end, and I recommend the use of substitution, although you can use other methods.
Well, so how did you work out R? I think that's what I've been on. So I did 4G, take 15.
So to work out R, I resolved for A vertically.
Yeah, 4G take 15 got 65.
Yes.
That's literally
32.9.
What's the choice? I'm so confused.
It's probably just finger trouble.
4 times 9.8
Yeah.
minus. Well, I did
15 times cos 65.
I did sine 25.
Sine 25, yeah, that's fine.
And I got 41.1.
You had radians.
Now, are you ready for part? Can you store store the value of A? So that was 4.385. So how do I do that if I've already got? Oh, I just divide my last answer by 2 and store that. So because here's part B. Nothing is working. My Bluetooth mouse has got to stop working. When B hits the ground, A carries on moving. So let's just remind ourselves when B hits the ground. It hits the ground when T is 2. Hi, George. So what we can do, and unfortunately with these examples I can't hide that, we can use SUVAT for A to work out how fast it was going when when B hits the ground, okay? So when B hits the ground, A carries on moving. So we're on, have you got your book today, George? We're on page 133.
Is it 2 seconds time? It is.
So it was 2 seconds. So we SUVAT up the situation. So it started from 0. The acceleration is that value we've got stored on our calculator.
So the accelerator at 4.39.
4.3, yeah, so hopefully you got that. And it goes for 2 seconds. So we want to work out how fast it's going.
And it's a distinct extensible. How can it keep moving?
So the string has gone slack, so there's no string, not being pulled anymore, is it?
So does inextensible not mean can't be compressed as well?
It can be compressed, yeah.
So,
What it means is no energy is lost in. So if it was stretchy, then you could argue that the acceleration would be the same. But if it's
Right.
inextensible, then the acceleration is always the same. So helpfully, they've given us that, but we need to make sure that's stored on our calculator, which is ironically the same as the distance. So I'm going to multiply it by 2 again. Don't know where I'm coming or going, and store that value. So this is how fast it's travelling at the point that B hits the ground. And we want to know how long does it take to stop. So what's going to now happen? Here's A. It was being pulled by this ring, this rope, but B's hit the ground, so that rope has gone slack. So what are the forces acting on A? It says that the forces stay the same. So what are those forces? Let's go back to my diagram.
just friction and one at 15.
Right, so we've got the 15 Newton force still pulling, and we've got friction.
But what is A not off the end of the plank yet?
No, no. So what we're assuming is that this is going to happen before it hits the end.
Yeah.
Okay, so there'd be some sort of indication that was going that doesn't happen.
Because there would be the forces would be completely different. Wouldn't they?
Yeah, yeah. Now nothing has changed, so F is still the value it was before. So we've got F, and we've got now hang on. So it's going to decelerate, isn't it? It's going to decelerate. We're going to get a negative acceleration. So what am I going to do? I'm going to say that that's the acceleration, but I know it's going to be negative. So I'm going to resolve this way. So I've got minus F minus 15 cos 25. I should have stored F in a different memory, stupidly. So I've got F up here somewhere. 23.00. So can I store that subsequently? I can't. Okay, I'm going to use 23. Because it's pretty close. And that's going to equal mass times acceleration, which is 4a.
What have you done that? So are you trying to work out U on the left?
No, no. I'm now using F equals ma to work out the new acceleration.
What is that then on the left?
So on the left is how fast it's travelling at the instant.
Yeah,
so
you're
that's
trying to work out-
sorry, that's the new u.
Yeah.
Yes, okay, the new u. So I know I'm using a rounded value, which is very bad, but it's 23.00.
So we're looking for how long it takes to sort of how far it is.
Yes. Sorry, did it say how long or how far?
How long until it?
How long? Right,
Until it
okay,
hits
so
the
we're looking
ground.
for time. We're looking for time. So I get my acceleration. which is negative because it's slowing it down, and then I'm back to Suvat. So you've got to get your direction correct. I've got that value stored. I've got that value stored. And I want to know t, that's u, isn't it? So that's the speed at the start of this part of the story, the velocity at the start of this part of the story. I want to know when v becomes 0, and it's time that I'm after.
So does that math equation just not account for like how rough A, or is it because A is a particle we're doing this work like that?
No, there's frictions involved. We've already calculated F, didn't we? We calculated it in the previous part of the question.
Does that not take account of how rough an object is? So when it's a box, you're just worried about the surface.
Yeah, no, it does. So they tell us here the coefficient of friction is 0.7. So that's a measure of how rough both the surface and the particle itself are.
So that's specific to the specific?
Yes. Yeah. Now the calculation of, I assumed that calculating coefficient of friction is something you did in physics, but clearly not. I seem to remember doing it when I was doing it. But anyway, it's not something we have to do. And because I've spent too long on this question, I'm going to cheat and look at the answer. So I'm hoping you can get something like 0.959 using those using the exact values, not rounded values. So I like these questions because there's an awful lot of, you've got to use your initiative, haven't you? You've got to use your initiative. We've got a number of techniques at our disposal, so we're really in Batman utility belt territory, and you know how much I like that. You know, which of my techniques am I going to whip out at this point and use?
Why was A decelerating after B before?
Okay, so to start, this is a two-part story, isn't it? Part one. B is pulling A. And so at the end of part one, bang, A is moving at 8.717 meters per second.
Yeah.
Okay? So the start of part two, A is moving at 8.771 meters per second, but it's no longer being tugged.
Yeah.
So all that's happening is it's being decelerated by these two forces, by the 15 newtons still pulling it back, and by friction, because it's still moving in that direction, so friction's still moving there. So what we then do is recalculate A using F equals ma, and then reuse Suvat. The V from the end of part one becomes the U at the start of part two. And we want to know when the velocity drops to 0, so we want to know when V is 0. So let's just have a look at example 3, and then over the page you can crack on with some of the practice questions if you want to. So try if you're looking at example 3 not to sort of be distracted by their method. See if you can do it. Again, we've got two separate entities, A and B, but they will share some things. Now in this case, they won't share acceleration, because this situation we're in limiting equilibrium. So there's no F equals ma here. It's force in one direction equals force in the other direction. What they will share though is T, is tension. So think about A, you can resolve parallel and perpendicular to the slope. Think about B, you can resolve vertically, no need to resolve horizontally for B. See if you can get somewhere with that. So no acceleration in this one. We're in equilibrium. I mean, we can use F equals ma, A0, so but I tend to use that, write that as forces one way equal forces the other.
accelerations at maximum.
Yes, so it's what's the bit in the question which tells us that?
Oh, it's the point of.
Yeah, so it saves that bit until there, but yeah, so we're in equilibrium, no acceleration. In the previous question there was an acceleration. So you could argue this is a bit more simple. What makes this more complicated are all the angles, but we can cope with that.
What you can't see, you just have T equal to mg.
Yes, simple as that. Simple as that.
Is there a part B to this question?
Have you not got your book?
No.
Is there a part B?
There is on the next page.
What does part B say?
Would MB if A were on the point of sliding down
Yeah, skip that. Go on to the X. Oh, you can't see the exercise, can you?
I'm actually finished this one, so.
Okay. I think the exercise is the same in the old book, so if I find it.
I've got book. I'm still doing it.
It's okay. It's okay. We're all good. We're all good. I'm sure I can find it in here. When you come to the exercises, could you skip question 2? Not that we're not going to do it, but That's a different sort of problem that I'd like to deal with next lesson.
Exercise 5.3.3, yeah.
Yeah, so 1 and then 3 don't each other. Yeah, so we won't do the second bit, we'll skip on to the exercise.
What did you get?
2.54 kilograms?
Yeah.
Yeah. You can do feel free to do part B if you'd wish, but I think it's worth jumping on. So 1 and 3 are similar sort of questions to the 2 examples that we've done. So that's over the page.